on Millikan's oil drop. Now, this is kind of a fundamental experiment when it comes to electric fields. That's Millikan's oil drop experiment, and parallel plates were used in them, and parallel plates are used all the time when you're dealing with charged particles because they're really, really nice to control the electric field. So remember, we talked about this a little bit, but when you have parallel plates, essentially you have a just like a plate on the top that's positively charged and a plate on the bottom that's negatively charged. Or, I mean, you could change it however you want. But regardless, you've got a positive and a negative plate with some space in between it. And why they're really nice is because if you hook this up to a battery, like so, we can control the electric field really easy. Okay, we can control the electric field really, really precisely. And why that's important is because in this middle section, you have a nice, uniform, and beautiful electric field, right? This is nice and uniform electric field based on what we do with the battery. So if we have, for an example, we put a proton up here by the positive plate, this proton is going to be repelled by the top plate, attracted to the bottom plate, and it is going to feel this electric force downwards, which means it's going to accelerate downwards towards the negative plate, which is awesome because it's going to accelerate at a uniform rate because we have a uniform electric field. So they're very useful when it comes to working with charged particles. Again, you do more with parallel plates in grade 12, but this is kind of the first introduction, and Millikan's oil drop is kind of a very nice idea and very nice experiment where they're used. So we can treat these types of examples when we're dealing with parallel plates as dynamics problems, and pretty simple ones, right? Where we know the sum of the forces acting on an object is equal to mass times acceleration. That's just our normal dynamics. But right now, right, if we think about this proton in those parallel plates, well, the sum of the forces acting on that proton is just going to be Fe, right? There's nothing else happening there, which means the sum of the forces is just going to be this electric force, which means the electric force must equal mass times acceleration. It must give some type of acceleration. So QE is equal to mass times acceleration, which, I mean, we could take that a whole bunch of different ways, but if you want, you could solve for the acceleration, which would be just QE divided by the mass, right? I'm going to highlight this formula, right? Because this one we can solve for whatever we want, right? We could solve for anything. Yes, we could specifically solve for the acceleration of an object by dividing by mass, but this right here, this idea that you have the electric force equal to mass times acceleration is huge because we can actually start doing some kinematics with our parallel plates and with our charged particles, okay? This formula, right, is mostly for our parallel plates, right, when it's in a uniform field, okay? If we don't have a uniform field, this does not work, and I'll add this up here, okay? This does not work for non-uniform fields. And that's because if the field is changing, that means the electric force is changing. And if the electric force is changing, that means the acceleration is changing. So actually, as an object accelerates away from something, the electric force and the rate of acceleration is actually going to decrease. So this really only works when you have a uniform electric field. Okay. Now, so let's see this in action. We've got two charged parallel plates create an electric field of 10 newtons per coulombs. A 4 times 10 to the negative 4 kilogram particle with a charge of 2 coulombs is placed between the plates. What is the acceleration of the particle? So this pretty much is exactly the same question as we just did. So let's go ahead, draw our parallel plates. This is going to be our positive plate. There's our negative plate. Let's put our particle right there. This thing is going to accelerate downwards like so, okay? Um, Inside this is a nice, beautiful 10 Newton per Coulomb electric field, right? So just like before, Fe is equal to mass times acceleration. So QE is equal to mass times acceleration, or acceleration is QE divided by the mass. Now we know what the charge is, right? We know what the charge is. We know what the electric field is. We're given the mass. So we can just go ahead and plug in all these values. We've got a 2 Coulomb charge in a 10 Newton per Coulomb field and a mass of 4 times 10 to the negative 4. So this thing is going to accelerate at a huge rate, 5 times 10 to the 4 meters per second squared, right? That is a huge acceleration, okay? And why is it huge? It's because the electric force is really, really strong, right? You've got a combination of a strong force with a small mass gives you a huge acceleration, okay? Now, some of you might be thinking, hey, well, what about gravity, right? Gravity is still pulling this thing down, but let's compare, right? If we just have an object with a mass of 4 times 10 to the negative 4 kilograms, well, that means that the force of gravity, which is just our mg, just like before, right? 4 times 10 to the negative 4 times 9.81, well, that's going to give us a force of gravity that's going to be equal to 3.9 times 10 to the negative 3 newtons, right? Okay. Compared to the electric force, we never actually calculated the electric force specifically, so we could go ahead and do that. 2 times 10, right? So the electric force is 20 newtons, okay? Well, if you compare those two values, right, gravity is tiny. Gravity is too small, so we don't care, okay? We don't care about it. Unless we design the experiment to specifically care about gravity, and that's where Millikan's oil drop comes in. So what Millikan did, and this was over 100 years ago in 1909, he asked two questions, okay? Is there a smallest unit of charge? And what is the magnitude of that elementary unit of charge? So think of this as Legos or building blocks, right? Or when you build something out of Legos, the overall thing is made up of a whole bunch of little Legos. But when you break it down, you see that the smallest block, right? Everything is just made up of one little tiny block. Kind of like a fence, right? Look at your fence. That fence is made up of a bunch of boards together that in total make up a big something, but can only be broken down as small as each individual board. So Millikan thought the same must be for charge. He said, if we have a bunch of charge, that must be made up of, like, you can't keep getting smaller and smaller charge. There has to be a limit, and there has to be something that is the smallest amount of charge that you can have. And he wanted to figure out what that was. So what he did is he used parallel plates, and he was able to suspend positively charged oil droplets between parallel plates. So what he did is he sprayed oil into a chamber, and these oil droplets, each individual oil droplets became charged. They then dropped through into a set of parallel plates with a nice, beautiful, even electric field inside here. And he was able to pick very specific oil drops and suspend them, okay? Make them float, because oil drops, if they're charged in a parallel plate apparatus, they're going to feel a force, but they're also going to drop because they have mass compared to gravity. So he was able to control it very, very precisely and watch these oil drops to balance it so that the force of gravity balanced out with the electric force. Okay, now this can be done like this one little thing about this positive and negative plates, right? It could be switched. It's not the end of the world. It doesn't matter, right? The idea is that some of these oil drops are positive, right? Some oil drops are positive, some are negative. So based on how you set it up, you can figure out if you're dealing with a positive or negative oil drop. That's not the main idea here. The main idea here is that he could suspend the drop perfectly so that the electric force equal to the force of gravity, which meant that you got a bunch of floating oil drops. Okay? And if he could do that, well, he knew that QE was equal to mg because they already knew what gravity was at that point. Now, with this stuff, okay, the electric field, he could find using the voltage, using the battery that he hooked it up to. The mass, right, he could find by using volume and density of oil, okay? Gravity they already knew, so the only thing left in this formula was this charge and what the charge on the drop was, okay? That was the idea. So he was able to solve for this and figure out, well, that Q would just be mg divided by the electric field that it was in. Okay, now remember on the last example, right? We said, oh my goodness, gravity is so small that we don't even care. Okay, but remember, if you design your experiment so that you do care, that takes care of everything, right? He designed it so that he would balance it, this electric field, with the force of gravity. Okay, so what he found that was that he found this unit charge. He found something that was the smallest amount of charge, which is what he was looking for in the first place. He called this the elementary charge, and it is equal to the charge of an electron. Okay? A lot of times in books, you might just see it like this, or you might just see it with E, and E is equal to 1.602 times 10 to the negative 19 coulombs. If we're talking about electrons, right, we're talking about the negative version. If we're talking about protons, we're talking about the positive version. But the magnitude of the charge is exactly the same. So whenever you have an amount of charge, it's always going to be made up of a bunch of electrons or a bunch of protons. Okay, so if we want to figure out what the total charge of an object is with how many elementary charges we have, it's just the charge, right? The total charge, I should say total charge, the number of, I'll say, for this case, I'm going to say electrons or protons, and then it's just the charge, right? Sorry, not just the charge. It's the whole reason why we're here. It's the elementary charge, that 1.602 times 10 to the negative 19 coulombs, okay? So that was a major discovery. Millikan essentially did the oil drop experiment to figure out what the charge of the electron was, and he was surprisingly accurate. He was ridiculously accurate for that time. Yeah, it's become a little bit more accurate as the years have gone on, but he was shockingly close back then. So this means that we could do some really cool things, right? In 1 coulomb of charge, right? In 1 coulomb of charge, okay, we want to know how many electrons are there. So 1 coulomb, if we look at this formula, we have our total charge divided by the elementary charge. We're going to get our 1 coulomb of charge divided by 1.602 times 10 to the negative 19. That means that in order to make this up, you have 6.24 times 10 to the 18 electrons. That is a huge, huge number of electrons, right? You need a ton of electrons, a ton of particles to make up charge, okay? So this question, more electrons, I'm going to leave this one for yours. You can do this one. This one's all you, okay? The answer, just so you know, is 7.2 times 10 to the negative 12 coulombs, but it's negative. Go ahead, try it. It's exactly the same idea as this first one, okay? Same thing with this one. This one's all you. We'll go over it in class. You need the answer is 2.4 times 10 to the negative 17 coulombs. There's the answer for you, okay? But that's not the important stuff. The important stuff is your oil drop and how we can use this to find it. So we have an oil drop that weighs 1.9 times 10 to the negative 15 newtons and is suspended in an electric field strength of 6 times 10 to the 3 newtons per coulomb. Top plate is positively charged, bottom plate is negative. What is the charge on this drop? Now, a couple things to notice about this question. Okay, I did it the tricky way. I gave you this as a force, right? This right here is your force of gravity already, okay? It is not your mass. Mass is in kilograms. Force of gravity is in newtons, which means mg, which is our force of gravity, is equal to 1.9 times 10 to the negative 15 newtons. Okay, sure, you could divide by gravity to find your mass, but you don't need that, right? Because we deal with mg. So if we have our apparatus, I mean, you can draw the picture. The picture gets kind of redundant after a while. Positive plate, negative plate. There is our oil drop like so, right? This oil drop, the force of gravity is bringing it down. The electric force is bringing it up, which means Fe is equal to actually, I'm going to do it the proper way, right? Sum of the forces here, going back to dynamics, is going to be Fe minus Fg, and that is going to equal to 0 because it's not moving, right? Just like our old dynamics, it's not moving because it's floating, so it's equal to 0. And that gives us the Fe equals Fg that we learned about and we love so much, which means, but we already know what our Fg is, so QE is equal to mg. So the charge on this drop right here is going to be Q. It's just our mg, or our force of gravity, divided by the electric field. So 1.9 times 10 to the negative 15 newtons, divided by our electric field of 6 times 10 to the 3 newtons per coulomb, which tells us that this thing has a charge of 3.16 times 10 to the negative 19 coulombs, okay? Tiny, tiny charge, which might not really seem like much, okay? But what Millikan was able to discover was that this drop has either excess electrons or it doesn't have enough electrons, okay? So if we take this charge, this Q value of 3.16 times 10 to the negative 19, and we divide it by the elementary charge of 1.602 times 10 to the negative 19, what we get is the number of electrons, and when you divide this, you get 2. You get 2 perfect electrons. Now, the thing here is you don't know if it's either an excess of electrons or it's missing some electrons. But based on how it's set up, okay, if we look at this thing, we look back at our picture, okay, if this thing was a positive charge, it would want to go down, right? This thing would want to go downwards. So that is not awesome, okay? And I'm going to turn that red because we need this thing to go upwards, which means if this thing is negative, would make it go up. right? It would make it be attracted to this top charge, this top positive plate, and it would balance, which means we have an excess of electrons, right? We're not missing some. We need this thing to have a negative charge. So we need a negative charge, therefore it has an excess of 2 electrons. Somehow 2 electrons hopped on for a piggyback and are hanging on to that oil drop, which allows it to balance in the field. That right there is Millikan's oil drop. You are going to do a lab on this based on in a separate sheet of paper, based on an online lab. It's fantastic. We'll go over that in class together. You've got a worksheet back down here, which has a little bit of everything as well as some Millikan stuff, but that is it for the unit, okay? That is it. So you've got these 2 questions to work on for yourself. Try some of the oil drop examples, look it over, maybe watch a video on it. It's pretty cool how he was able to do it, and we will go over it in more detail tomorrow.